a young fellow called Harris Pirie, right? So currently at Oxford University, and the title of the talk is Visualizing the Origin of Bulk Metallicity in the Topological Kondo Insulator Samarium Hexaboride.
That's right.
Thanks for being here.
Yeah, thank you. Thank you for having me. And thanks to the organizers for inviting me to sunny California. It's much better than Oxford at this time of year, so I'm appreciating the sunshine while I have the chance. So today I want to tell you a little bit about our measurements in samarium hexaboride. So this data was taken when I was a PhD student in Jenny Hoffman's lab at Harvard, and also in the lab of Seamus Davis, where I'm currently a postdoc. And I want to acknowledge the theoretical support we've had from Dirk Moore and his student Eric Mascott. Let me start by introducing the main actor in the play. This is samarium hexaboride, a stoichiometrically simple compound with a complicated past. And I think it's worth appreciating that this tiny black rock has sparked many decades of lively debate and has significantly furthered our understanding of interacting quantum phases. So in the early days, the debates were about whether the low temperature conductivity came from impurity states or from surface states. When the surface states were shown fairly definitively, the debate shifted to whether they were topological or not. And today's question, I think, is even more basic. It's whether samarium hexaboride is even an insulator at all. So anyone with a voltmeter should be able to answer that question, right? But it's going to turn out to be a little bit more complicated. So this is the outline of my talk today. I'm going to spend a little bit of time showing you the essential physics and recapping our previous results on the topological states in SMB6. But the bulk of the talk is going to be about our observation of metallicity within the insulating phase. And then if I have time at the end, I'll try and connect these two observations. Great. So the early interest in SMB6 came from an anomaly in its low temperature conductivity. So I'm going to walk you through it kind of slowly. At high temperature, samarium hexaboride is just a normal metal. But unlike most other metals, in addition to the conducting 5d electrons that form the parabolic band, there is a lattice of local 4f moments, one at every site. And through the Kondo process, they're renormalized to the chemical potential. And if you zoom way in, they're also split by crystal field interactions. So what happens as you cool down this material is that the 5d electrons start to coherently screen the 4f moments. This generates Kondo singlets at every lattice site, and that interaction opens up, creates an avoided crossing and opens a gap at the chemical potential. So that gap drives up the resistivity, and this phase is a Kondo insulator. I'm sure you're familiar with it. It's an interaction-driven insulating phase. The anomaly is that at the lowest temperatures, this divergence of the resistivity suddenly flatlines, it plateaus. And some transport measurements were able to show that in this low temperature region, the conductance is coming almost entirely from the surface. So they just change the ratios of surface to bulk thickness and look at how the plateau responds. This observation led to the prediction that samarium hexaboride could be an example of an interaction-driven topological phase, whereby this gap, which opens due to the interactions, also encodes a non-trivial topological invariance and therefore hosts heavy Dirac surface states. These surface states have to be heavy because they need to connect the conduction band and the valence band, and the gap that they have to do so is really small. So they're going to need to traverse really quickly. What followed from this prediction was really a marathon of experimental effort. A number of transport papers quickly confirmed that there were surface states in SMB6, but they themselves can't measure the velocity. So there were follow-up experiments by photo emission and quantum oscillations, each of which detect surface states, but with velocities that are orders of magnitude too fast. About 10 times too fast in photo emission, about 100 times too fast in quantum oscillations. So I'm going to take a moment to step through each of these two experimental techniques, and then I'll show you what we see with our STM. One of the key challenges for any surface-sensitive probe looking for surface states in SMB6 is that SMB6 is a rock. It is a solid material that is very difficult to cleave, and it doesn't polish very well. So you end up with surfaces that are typically very messy. This is an SEM image. And not only are they difficult to cleave, but when you do cleave them, there's also polar and non-polar ways in which you can terminate the surface. Actually, the most basic way that you would cut this crystal in half leaves an excess charge on the surface that draws electrons from the bulk, and it affects the electronic structure on this surface. You can also terminate the crystal in a non-polar way by removing half of the samarium atoms from the surface, but neither of these is particularly energetically favorable over the other. So what you end up with is really small ordered patches. So here I've drawn the largest one that's ever been seen. It's about 80 nanometers. This is a single uniform termination. And I've drawn that to scale with a typical photo emission spot size. So my point here is that the photo emission experiments are certainly measuring the different polar and non-polar surfaces. So we had a postdoc in our lab, Christian Matt, who took some of those early photo emission experiments. And together we built a simulator to try and replicate what ARPAs would see based on STM results on each of these terminations if you just did a simple 50-50 mix. So this is comparing to the actual experiment, and our simulation captures the basic result, which is that we see enhanced velocities of the surface states, and the Dirac point disappears. So I was actually quite surprised by how well this crude simulation was able to capture the essential physics of the photo emission data, and that's informing our understanding that photo emission is measuring some average of polar and non-polar terminations. When the de Haas van Alphen results came out, they seemed to indicate a two-dimensional Fermi surface, which is consistent with surface states, but with effective masses that are lighter than the bare electron mass. So what I need to tell you about this set of measurements is that the samples that they use contain an aluminum flux. This is just included in part of the growth process. And what that can do is sometimes leave inclusions within the sample. These are aluminum inclusions. So this nice paper came out a couple of years ago from the group at Los Alamos, where they polished down one of those samples until they removed the very last one of the aluminum inclusions. And what they find is that the quantum oscillation signal just suddenly disappears when you get rid of the aluminum. So the suggestion from this paper is that the de Haas van Alphen oscillations in SMB6 are actually coming from embedded aluminum. Okay, so the summary is that there's been two techniques that have tried to measure the surface states in SMB6, but neither of them have found the heavy surface states that were predicted. So what do we need to image them? I think the most important thing is that we need a spatially resolved probe so that we can find a single non-polar termination. We also need access to the filled and the empty states because the hybridization gap opens around the chemical potential. We need to do so with millivolt energy resolution and real and momentum space resolution as well. This full set of experimental requirements is met with a scanning tunneling microscope, and this is the one in Jenny Hoffman's lab that I used to take the SMB6 data. Here are some of our images of the non-polar regions of SMB6. You can see these rows of atoms, and every other row is missing, which is why we identify it as this, I'll sometimes call this the 2x1 reconstruction. So on that surface, we measured the DIDV, the differential conductance. That's proportional to the density of states, and we can measure this with angstrom scale spatial resolution and millivolt energy resolution. So a map like this will take 3 to 4 days to record. Everything has to stay exactly still while it does. But when you come back, it contains an enormous amount of information about the wave functions in the system. One of the ways we get at that information is by looking for quasi-particle interference patterns. So these are standing wave patterns that form around defects, as incoming momentum eigenstates interfere with scattered momentum eigenstates. If we can identify these patterns and measure their energy-dependent wave vector, then we can usually infer the underlying dispersion relationship in the sample. So in practice, we do all of that by taking a Fourier transform. So here is 6 independent measurements of a cut in the Fourier transform differential conductance. So I've got a specific momentum direction along the x-axis, energy along the y-axis. These measurements were taken on 3 different samples with different dopants and grown by different collaborators, but they all show the same key features. And there is kind of a lot going on, which I've indicated with all of these dashed lines. But the main thing I want you to focus on is what's in green. So this is a quasi-particle interference pattern that starts out with a wave vector that matches the Bragg peak. It disperses in towards the center and back out again. That's covering 50% of the Brion zone, and it does so in 10 millivolts. So this is an extremely flat band that we have measured. If I isolate just that one signal from the measurement and put it in context with the band structure, what we see are linearly dispersing surface states within the bulk hybridization gap with a measured velocity that is within a factor of 2 of the original predictions. Okay, so I just want to summarize by saying that by focusing on a non-polar surface in SMB6, we were able to image the predicted heavy Dirac fermions. Okay, now let me jump into the metallicity. So the starting point for this is to tell you that when I went through the quantum oscillation story, I really only told you half of that story, because there is another way to measure, to grow samarium hexaboride that doesn't use any aluminum flux at all. The price that you pay is that you typically get a little bit more vacancies, but the quantum oscillation signal doesn't go away. It actually gets even stronger. And this signal is a little bit different too. If you map its angular dependence, it looks like a 3-dimensional Fermi surface. So this is a bulk Fermi surface existing in samarium hexaboride at 400 millikelvin. And that's a real problem because samarium hexaboride is an excellent insulator. It should not have a bulk Fermi surface. Here are some clever Corbino transport measurements from the group at Michigan, where they're able to track the bulk resistivity even in the low temperature regime where it's dominated by surface conduction. What they find is that in pure samples, the bulk resistivity just keeps going up and up, diverges by 10 orders of magnitude as you cool down from 15 Kelvin. So this is a robust DC insulator. And what that led to was some quite eye-catching press when the quantum oscillations were first announced about how we've found this material that both conducts electricity and doesn't conduct electricity. But it's not just quantum oscillations that see some form of metallicity in floating zone grown SMB6. Early on, it was noticed that there's an increase in the low temperature linear specific heat. That's usually associated with the presence of a Fermi surface. There's also an anomalous AC optical conductivity. And most recently, there have been results from Compton scattering, which roughly measures the total charge in the Brion zone. So if it's an insulator, you would expect it to be a flat line. What you actually see looks more like, it is a slight deviation, and it looks more like a scaled version of lanthanum hexaboride than it does an insulator. So both the Compton scattering results and the quantum oscillation results allow you to extract what the Fermi surface looks like. And in both cases, it looks like the metallic parent state of SMB6, so the high temperature D electrons, essentially with no influence from the F electrons. As you might imagine, this generated quite a lot of interest theoretically, and I'm just plotting the proposals chronologically. So to begin with, there was all the explanations seem to suggest that this was an intrinsic effect in SMB6, and more recently, there there have been a number of papers that have suggested that maybe this is extrinsic. That means it's coming from defects. And in that case, there would be some microscopic metallic puddles that we could go looking for. I think it's fair to say there's no theoretical consensus yet. So I'm going to approach this question experimentally and see if I can find microscopic evidence of light electrons in samarium hexaboride. Our specific motivation for this study was an older paper from Dirk Moore's group, where they looked at a defect called a Kondo hole. A Kondo hole is just what happens when you remove one of the F moments from an otherwise compensated Kondo lattice. And in that case, what they found is that you get oscillations around the Kondo hole in the conduction electron density, in the hybridization strength, and in the magnetic susceptibility, and that those responses reflect the properties of the conduction band. So this is a very non-intuitive result. It's saying that you have a response at a conduction band wave vector, even though those momentum eigenstates are completely gapped in the system. So I'm going to spend a few slides to walk through this pedagogically to try and give you a sense of why you might expect this. The question is, what happens when we remove one F moment from a Kondo lattice? So the first thing that happens is the electrons that were previously screening that F moment, well, they don't need to be there anymore. So they're free to redistribute throughout the rest of the lattice. Maybe you get more of them over here and less of them on site, and they set up oscillations in the conduction electron density. This is essentially a Friedel response of the screening cloud to the missing F moment. Now, one consequence of this is that if you have more electrons at a particular point, each one of those electrons needs to do a little bit less to screen the magnetic moment. So you might expect also oscillations in the interaction strength, and those oscillations should be out of phase. Those are already observed in this compound, uranium ruthenium 2 silicon 2, by measuring the hybridization gap. As you move away from a Kondo hole, it's found to oscillate with this wave vector. The last thing I want to draw your attention to is that in the places where you have more electrons that are doing less, they're more free to respond to an external magnetic field. So you might also suspect that you would get oscillations in the magnetic susceptibility. The important point about this response is that it characterizes how the screening cloud has redistributed itself, not how the heavy fermion ground state has redistributed itself. So the wave vectors of this response are those of the conduction band, not those of the heavy fermion bands. Okay, so what would we need to try and measure this? Well, we're going to need nanometer scale spatial resolution, millivolt energy resolution, and sub-Kelvin temperatures. We have all of that. We also need charge sensitivity in order to see this first order response. And an STM measures the energy resolved density of states, but not the energy integrated density of states that you need to detect the local charge. So I want to explain how we get around that problem in heavy fermion lattices. This took us a really long time to understand, so I'm going to try and go through it slowly. The key thing to think about is what happens when you add charge to a Kondo lattice. And that turns out to be different from how you might dope a different material. The main thing you have to keep in mind is that as you add charge carriers, you don't change the number of F moments. There's still going to be one of them at every site. The reason that's non-trivial is because the Fermi surface does contain F orbital character. It got there from the Kondo renormalization. So if you tried to naively dope this system by dragging the Fermi level up or down, you would change the amount of integrated F orbital character, so the total amount of grayness here, and that would violate this constraint up here. So what has to happen instead is that as you change the size of the Fermi surface, the Kondo resonance must adjust its energy position in order to conserve the total F orbital character. We calculated this response in a Kondo lattice model, and we found that it was fairly linear over a wide range of charge doping and over a wide range of parameters that you put into the model. So the point here is that we can use the Kondo resonance as sort of an inbuilt charge sensor. if we can measure its energy position at every point in space, then we can infer what the excess charge is at that point. So we're using this axis to measure this axis. So here's what that might look like in our experiment. The Kondo resonance shows up as a peak dip feature. It's a Fano resonance. And as we add additional charge, this is the calculation, the position of the peak shifts just a little bit towards the Fermi level. Now these shifts are quite small, so we're going to do a little trick. The trick is that because they're so close to the Fermi level, if you change them just a little bit, it dramatically changes the asymmetry, the particle hole asymmetry of the IV curves, such that if we calculate this ratio, the ratio of forward tunneling current to backward tunneling current, that's called the rectification, you translate these small energy shifts into large amplitude variations. Now, in practice, this is a much easier thing to measure experimentally. And so I just want to tell you the logic of why I'm looking at this quantity. This amplitude variations track the energy position of this peak, which in turn tracks the local charge. That's our argument. Okay, that works in theory, but will it work in practice? So the first thing I want to look at is a test case, this compound uranium, ruthenium 2, silicon 2, because a lot of the wave vectors are known already in this material. At high temperatures, you have a light band, and it splits into two heavy bands as you cool down below about 16 Kelvin. This is our DIDV measurement of the Fano resonance on the uranium surface of URS in a sample that contains a few thorium dopants. Those thorium dopants are already known to act as Kondo holes. If we move close to one of them, we see that the peak in the DIDV curve does shift just a little bit. So this is a sub-millivolt shift, and actually even in this cluster of gray curves, the peak is still moving, but it's barely measurable. When I calculate this ratio of tunneling currents, those small shifts in peak position translate into large amplitude variations. And if I map this quantity as a function of space, I see clear oscillations that emanate from the position of these thorium dopants. In the Fourier transform, they show up as a sharp ring, and the wave vector of this ring precisely matches what was measured previously in this compound and is what you get for the light band. In contrast, we can also do our usual DIDV measurement, identify quasi-particle interference patterns, and track their energy-dependent wave vector. And in that case, we see a Fermi surface composed of heavy fermions. As an experimentalist, I find this really weird. We did one measurement. We measured both of these quantities. It's the same data. And when you look at DIDV, the differential conductance, you see the heavy fermions with some specific wavelength. And then you look at a different quantity, the rectification, and you see the Kondo screening cloud with a totally different wavelength. It's a very weird result, but it's true. Okay, so now I'm going to follow exactly the same set of steps, but with a different material in the microscope. Here is the band structure of SMB6. At high temperatures, it has this light band, and at low temperatures, it has heavy Dirac fermions rather than heavy fermions, but otherwise the analysis is going to be just the same as in URS. In SMB6, we get a few different kinds of dopants. Here is an image of an iron dopant and a samarium vacancy. Both of these dopants replace a samarium F moment, and so we would expect both of them to behave as Kondo holes. As we walk towards the iron dopant, we're measuring the DIDV. We can see the Kondo resonance, and we can see that it changes position. It's clearest about here, and it actually seems to oscillate back and forth. These small energy positions translate into large amplitude variations in the measured rectification ratio, such that when I form a map of this image, I get this rich structure around those two defects. So I'm interpreting this image as a map of the local charge environment around a Kondo hole. And the most distinct feature I can see are these oscillations shown in the line cut with very high signal to noise. If I look at those oscillations in a Fourier transform, they show up as this sharp ring. You can see it here. And the wave vector of this ring matches that of the light band and is distinct from what we measure simultaneously from the heavy Dirac fermions. So I want to put this in context. These dashed lines are the high temperature Fermi surface measured by photo emission. These are the metallic wave vectors that quantum oscillations has measured. And you can see they lie right on top of our data. So the summary here is that by measuring small shifts in the position of the Kondo resonance, we were able to identify regions of the samples that contain light electrons, specifically the regions around Kondo holes. Okay, just in the last couple of minutes, I want to try and connect these two measurements and say something more concrete about how we can connect these Kondo holes to the de Haasvan-Alphen oscillations. So at the very minimum we need to show is that if these holes were to contribute to de Haasvan-Alphen magnetic quantum oscillations, they must have a finite magnetic susceptibility. That's all I'm going to try and show. And in order to show this, I'm going to invert a common argument in topological materials. So the usual argument goes that if you have a defect that's magnetic, it's able to spin flip scatter topological states, and that gives you a backscattering contribution. And I think the nicest experimental observation of that is in this bismuth bilayer system, where if you put iron clusters on the edge, you scatter the one-dimensional topological edge state, and you create this additional backscattering wave vector in the QPI pattern that is completely absent in the case that you don't have those magnetic clusters. So I'm going to invert this argument. I'm going to say if I find a backscattering wave vector, then I can infer that the defect that caused it must have some local magnetism. So here is an area in SMB6 that is three terminations, 3 terraces of the 2x1 reconstruction. And this area contains 15 well-isolated Kondo holes, either the samarium vacancy type or the iron dopants that I showed you before. In this region, we measured the Fourier transform differential conductance, exactly the same as before. We see the heavy Dirac fermions, like we did before. But what I glossed over before is that the scattering process that generates this signal is quasi-particle backscattering. That's the only one that makes sense. So the question is, where in real space does this signal come from? And to answer that, all you need to do is inverse Fourier transform this data at the wave vector that corresponds to the heavy Dirac fermions. Then you form this map of the locations in real space that are strong scattering centers, strong backscattering centers for topological states, which I'm using as a proxy for local magnetism. So if I overlay the topographic data on that map of local magnetism, you can see that everywhere that we've identified one of these Kondo holes, there is a corresponding peak in the local magnetic structure. So taken together, these two measurements give us confidence that the Kondo holes could contribute to the de Haasvan-Alphen oscillations that have been measured. Okay, in conclusion, STM sees a consistent but rich picture in SMB6, whereby the Kondo mechanism generates both the topologically emergent heavy Dirac fermions and the metallic puddles that give rise to some of the interesting properties recently measured. Thank you for your attention.
And stunning data. Questions? Yes.
Thank you, beautiful talk. I have a question regarding the way you determine that you have light particles around Kondo holes.
Yes.
So maybe if you can go back to the slide with the YRS, that's was a bit more summarized than the. So yeah. So sorry, URS. Yes. Yeah. Thank you. So what you're measuring is you're measuring at the voltage of 3 millielectron volts.
Yes.
Which I translate to 30 Kelvin.
Yes.
And at the same time, you say that heavy fermions, sort of the heavy fermion physics only appears below 16 Kelvin.
Yes.
So isn't it automatic then that you would always measure only light particles, or is there a catch in the way that I'm thinking?
Well, this measurement is taken at 0 millivolt and measures heavy fermions. So you can measure them both.
You can measure them both, even if the voltage is high enough.
Yeah.
It's higher.
So actually, I didn't really comment too much on the voltage I used here because it doesn't really matter. I could take this measurement at 3, at 2, at -1, anything, and it looks identical. Basically, any voltage within the hybridization gap, within from here to here, and this metric is dominated by the position of those peaks. So as they shift, this changes. If I look at this bias, or this bias, or this bias, I can't look at 0 for divide by 0 errors, but otherwise, it's identical. It doesn't matter. Yeah.
Okay, thank you.
Hi, I have a question about length scales. The Kondo hole, which is just like around an impurity, must be on like a nanometer scale.
Yeah.
And then what about the oscillations? When you are looking at the de Haas-Van oscillations, that must be a much larger length scale.
Yeah, I have a couple of comments about that. So that's a really good question. Yeah, the length scale that we see is a few nanometers for these puddles. Yet the quantum oscillations have a cyclotron orbit with a radius of 100 nanometers. So they seem like very different things. However, the cyclotron orbit comes from a semi-classical picture of the electrons. And that semi-classical picture already doesn't work very well. For example, the scattering length should be larger. The cyclotron orbit should be larger than the scattering length in order to see quantum oscillations, but it's not. The scattering length suggests that the quantum oscillations signal, they only move about 10 nanometers before they scatter, whereas they should really be moving more than 100 nanometers to form cyclotron orbits. So I think whichever way you look at this, the quantum oscillations are definitely unconventional. And so whether you're applying a semi-classical notion or something more exotic like these Kondo holes, I think either way, it's not perfect.
Right, but I don't have to use theory. I'm just saying from the experiment, you would extract two different length scales.
Well, so there is many experiments extract many different length scales. If you look at the thermal conductivity, the length scale you get for the mean free path is about 10 nanometers. That's consistent with this picture. Yeah, if you look at the Dingle factor from quantum oscillations, the length scale is like 50 nanometers for the mean free path. Yeah. So it's difficult to say, I think.
Yeah. Okay, thank you.
Yeah, great talk. Thank you. I'm trying to understand the picture that you're showing with the Kondo holes is on the heavy surface state. That is, it's the topologically protected surface state. So in samarium hexaboride, actually the heavy surface is actually an insulator. There is no surface in the bulk. So I'm trying to understand like how you translate what you're seeing on the surface state to the physics of the bulk.
Yeah, it's a really good question. So it would have been better if we had done this experiment in the bulk, for sure. But that's not possible. Sure. Every time we cleave it, we get the surface state. So I've separated the talk to kind of, not overlap them too much. And that's a bit convenient because in reality, the surface state is there whilst we're doing this measurement. But it's kind of weird how it interacts with this object, because it is both suppressed and scattered as you get closer to this magnetic object. It's suppressed by around 50% in this region where we see these metallic puddles. And that's also the region where we see the backscattering. So exactly how that process happens, I don't know. In this measurement, they're over the top of each other. It's unavoidable.
Just go to the center and you get it back.
Yeah, so probably following up on what other people have asked. So the picture that you have based on these measurements is that in the bulk you have Kondo holes, and around Kondo holes in some region of few nanometers, there are metallic puddles, and they don't percolate, so you get an insulator. Now, I don't know what to expect, but so the idea is that these puddles are giving you the magnetization oscillations. Should one also expect to get Shubnikov-de-Haas? As you know, that's not seen in any of the experiments. Sorry?
Yeah,
yeah, it's puddles, but nevertheless, things are moving around like this, and they're hopping from one orbit to the other.
Yeah, so
I don't know what to
depends
expect.
on how they overlap with one another and whether you end up with large enough regions to see some kind of oscillations in the resistivity. If they're non-percolative, it's not clear to me that you would see Shubnikov-de-Haas oscillations from these objects.
Yeah, no, it's not clear to me either,
Yeah.
but I wonder if there's some.
It's a good thought.
To follow. So another question: if the bulk is really inhomogeneous on that several nanometer scale,
Yeah.
That should show up in things like NMR, right? There's a broadening of the line. Again, my understanding is that the NMR lines are very, very narrow.
I don't have the NMR data clear in my head. I think they see something. Yeah, I'm not sure. I have to look into that. That's a good point. Yeah, let me check the NMR.
Nice talk, Harry. So I think I have a question which is sort of similar to what Philip asked. The samarium hexaboride seems to have a lot of entropy mid-gap. And so I was wondering whether from the surface measurement you could have some estimate of what the bulk Kondo hole concentration would be, and is there enough spectral weight to explain the observed entropy?
The specific heat, yeah.
Yeah.
My thoughts about the specific heat is that it seems to vary a lot, sample to sample. Mm-hmm. So it's kind of hard, like what is the number that I'm trying to estimate for? And in samples where you add a small concentration of magnetic dopants, the specific heat, the low temperature specific heat goes wild in those samples. You only need a few % of magnetic dopants. So it seems plausible, but I have not done the quantitative analysis that you're asking.
In principle, is it possible to constrain?
Seems it to me, but I haven't done the numbers.
Okay, thank you.
Okay. Other questions? Okay.
Thanks. I guess I was curious also about the first part of the talk with the polar, the averaging of the polar and non-polar surfaces. So what does the QPI on the polar surface look like?
Yeah, we don't have QPI on the polar surface. So I say that's a pretty crude simulation, and it really is. Let me show you the data that we're using to build that. Okay, that's right here. The polar surfaces that we found are really small. They're too small to have coherent scattering, so we don't see anything conclusive in the QPI. What we do see is the Kondo resonance and another lower F resonance. And we can measure those on the 2x1 surface, the non-polar surface, and on the polar 1x1 surface. And we find that they seem to be rigidly shifted downwards. Something more complicated is definitely happening. This is a stupid model. But in this stupid model, all I do is shift the occupied states downwards by this amount that we observe, and then average these two things together, put it in two different detectors, and it looks similar enough to the photo emission data to be a proof of principle. That's the argument.
Thanks.
Okay, let me take the last question. So, I mean, I've been asking that for very long. So, samarium is strongly mixed valent. Everyone just says Kondo, Kondo, Kondo.
Yeah.
So, what's your comment? It's not Kondo, in fact, it's mixed valent. So, of course, it's not really quite the same. Maybe STM is too slow to see the difference, I guess, right?
I think that's my perspective, yeah, is that unless there's something I could measure that would help me comment on that debate, I'm sort of agnostic to what's the key physics. My pictures are easier to understand from the Kondo side than having to think about the complications from mixed valence. And if I don't have to think about a complication, I don't. But that's probably not the best answer. Yeah.
Yeah, I don't have the answer either. So I think it's just STM will average, right, in terms of time.
Definitely,
And you see sort of effectively a Kondo.
Yeah.
Okay, if there's no further question, we move to the coffee break and thank the speakers again.